Lecture 7 is all about L'Hopital's rule and how to use it to determine limits which are indeterminate in form. So here we have two basic indeterminate forms. We have an indeterminate form of type 0 over 0 is a limit of a quotient of two functions which both approach 0 in the limit. So for example, we have the limit as x goes to 0 of e to the x minus 1 over sine x is indeterminate of type 0 over 0 because both e to the x minus 1 and sine of x are approaching 0 as x approaches 0. And this produces two different forces on the quotient. As sine of x gets smaller, the quotient gets larger, but also as e to the x gets smaller, the quotient gets smaller. So the question is, which of those forces wins? Also, an indeterminate form of type infinity over infinity is a limit of a quotient f of x over g of x, where f of x approaches either plus or minus infinity, and g of x also approaches either plus or minus infinity. So an example here is the limit as x goes to infinity of this polynomial over e to the x. And of course the polynomial is approaching infinity as x goes to infinity, so also is e to the x, but as we know from class, e to the x is getting there at a much faster rate, so in fact we'll see using L'Hopital's rule that this limit is 0. We can apply L'Hopital's rule to many of these situations. We have the fine print here at the bottom saying when we can apply it, and we can do that certainly as long as both functions are differentiable if around a, where I'm taking the limit as x tends to a, as long as both functions are differentiable in some open interval except possibly at a, around a, however small that interval might be. And there's one extra condition: we also must have some such interval where the derivative of g is not 0 in that interval. If the fine print is fulfilled, or if those conditions are fulfilled, then if I let limit stand for any one of these limits, and suppose I have an indeterminate form of type 0 over 0 or infinity over infinity, then L'Hopital says that the limit of the quotient, f of x over g of x, is the limit of the quotient of the derivatives. And quite often this quotient of the derivatives is no longer indeterminate, and we can figure out what the limit is. Let's go back to our example, e to the x minus 1 over sine x. What is the limit as x approaches 0? Well, we can apply L'Hopital here. First we must check that it is an indeterminate form, and we did that before. It's an indeterminate form of type 0 over 0. And we can apply L'Hopital's rule because both of these functions are differentiable everywhere, especially around 0. And the derivative of sine of x is cosine of x, which doesn't get anywhere near 0 for x near 0. So if we apply L'Hopital's rule, L'Hopital says that the limit as x goes to 0 of e to the x minus 1 over sine x is the limit of the quotient of the derivatives. And that's the limit of e to the x over cosine of x. And both of those approach 1 as x approaches 0, so the limit is 1. Another indeterminate form is a limit of the form the limit of f of x times g of x, where one of those functions goes to 0 and the other goes to either plus or minus infinity. And again, this gives us two opposing forces on the product. One function is going to 0, making it smaller, and the other is going to infinity, making it larger in absolute value. Here's an example. The limit as x goes to infinity of x times tangent 1 over x. We see the tangent 1 over x is going to 0, and the x is going to infinity. And we can convert these limits to indeterminate forms of type 0 over 0 or infinity over infinity, and we choose which one depending on which one makes differentiation easier. And if I want to convert f of x times g of x to an indeterminate form of type 0 over 0, I write it as f of x over 1 over g of x. And because the g of x is going to infinity, plus or minus infinity, 1 over g of x is going to 0 in the limit. I could also convert to the type infinity over infinity by writing this product as g of x over 1 over f of x, and now the 1 over f of x is going to infinity because f of x is going to 0. And then I can go ahead and apply L'Hopital's rule as I did before. Here's an example. Our example, x times tangent 1 over x. I can convert this to an indeterminate form of type 0 over 0 by writing it in the form tangent 1 over x, which goes to 0, divided by 1 over x. And this quotient is equal to the product x times tangent 1 over x, and this is an indeterminate form of type 0 over 0, and I can apply L'Hopital as I did before. Here are 3 other types of indeterminate forms. If I have a limit of f of x to the power of g of x, where f of x is going to 0 and g of x is going to 0, then that limit is indeterminate. Why is it indeterminate? Because the f of x is getting smaller as x tends to wherever it goes in the limit, and also the power is getting smaller. And you see, for numbers near 0, a smaller power is going to make them larger. And so we have 2 opposing forces. We have the base here going to 0, and the power is going to 0, making this f of x to the g of x larger, and the base is making it smaller, so we can't really tell where this limit is going. But we'll see we can apply L'Hopital's rule here. Another indeterminate form is infinity to the power of 0, and also 1 to the power of infinity. So how do we deal with these indeterminate forms? Basically, we start by looking at the logarithm, the limit of the logarithm of f of x to the g of x. So the limit of the natural log of f of x to the g of x is the limit of g of x times the natural log of f of x. And you'll see that in all of these cases, this will give us an indeterminate form of type 0 times infinity, which in turn I can convert to an indeterminate form of type 0 over 0, or infinity over infinity, and hopefully calculate with L'Hopital's rule. Suppose I calculate that limit, and I find that it's alpha. Then I have the limit of my original limit is the limit of f of x to the power of g of x, which is the limit of e to the power of the natural log of f of x to the g of x. And you can see that on the previous line I've calculated the limit of this power and called it alpha. Because the exponential is continuous, the limit of e to the power of this function is e to the power of the limit of the function. So we get that this limit is e to the alpha. So I can interchange e with the limit there, and since I've already calculated the limit of the power, I can use that to find that the limit of f of x to the g of x is e to the alpha. Lastly, we have indeterminate forms of type infinity minus infinity. And again, we can easily see the 2 different forces acting on these types of limits, if I have the limit of f of x minus g of x, where f of x is going to infinity and g of x is going to infinity, then f of x is getting larger. I'm subtracting off something that's getting larger. So question is, what happens to this limit? Does it go to infinity, or does it stabilize at something finite? And to deal with these limits, we do whatever we can to convert to a quotient or to some indeterminate form of the previous types. For example, if I have two fractions here, I could add the fractions. So here we see this is an indeterminate form. As x goes to 0, from the right, 1 over x goes to infinity. And also 1 over sine of x is going to infinity. But I can amalgamate these two fractions, and I multiply the denominators. And then I get the numerator as sine of x minus x. And now I see I have the limit as x goes to 0 of something going to 0 here. And we also have sine of x minus x is going to 0. So we have a limit of type 0 over 0, or an indeterminate form of type 0 over 0, to which I can apply L'Hopital.